Hello everyone. I want to pick up from where we left off last day. We were looking at flip-flops and latches, and I just want to revisit that a bit more today and talk about using them and in a means that is maybe more representative of how we're going to see them in our computer systems. So if I just bring in the image of my D latch on the right, so this being my latch, this being my flip-flop, the difference being the latch is level triggered, whereas my flip-flop is edge triggered. Okay, let's again look at the timing diagram for these. I'm just going to pull one out of the class notes this time. So if we grab this timing diagram, it's actually figure 1.18 from the class notes, and let's just look at this again and remind ourselves what's going on here. So we refer to, and this is specific to the latch, so the circuit on the right. So okay, so this timing diagram is this timing diagram is the one associated with the latch here. Okay, so again, we can see the input signal to the latch shown as the signal D here, and it's cycling back and forth, and you know, that's not, it doesn't have to be like that, and this is just for this example. And we see how the enable signal is determining what gets through to the output. Okay, so when the device is enabled, so during this phase, the output Q here simply follows the input. Okay, and we see a few instances of that where when my latch is enabled, my Q simply follows my input D. But you know, in reference to the name, the latch, the data is actually latched or held on the output when I'm actually when my enable signal is inactive. So during these phases is when my data is actually latched. So my data at the output is not changing from the state that it was at when the enable signal went to the inactive state. So whatever my D input was here when I transition from an enabled state to a latch state, that is retained on the output. So in this case, at this point right here, I'm high, so Q is high, then I go to a disabled state down here, so Q stays high. And then in this case, the next time my latch goes from enabled to disabled, my input here is low, so from this point on it stays low because it's latched in that state. Okay, let's look at the same thing for a timing diagram for a flip-flop that has a very should I say similar signals applied, so same type of D input, and let's look at how it responds to the clock input and how that impacts the output Q. Okay, so here we have D just cycling back and forth between high and low again, and now we see that this device is edge triggered, and rising edge triggered corresponding to the rising edge triggered device that we have above here. Okay, so here we showed rising edge triggered device. Okay, so this was rising edge triggered. So we see that the key points of interest are when these rising edges are occurring. Okay, so that's the cause of the change on the output. Okay, so in the case of the flip-flop, the major difference is that the flip-flop only changes states on the output of my flip-flop only changes state when that edge occurs, in this case a rising edge. So it's only at this specific instance that whatever the state of my input is gets copied to my output. So my output becomes high here. Okay, and then again on the next rising edge, I have a rising edge here that takes the value from the input and copies it to the output. So my output ends up going low. But you'll note that between these rising edges, or these edges, whether they're rising or falling, depending on the flip-flop, the output is latched. So the output cannot change other than in this kind of this time window here where I have these edges occurring. Outside of that, where that edge is occurring, the device is latched. Okay, so that's a little the key difference between our D latch versus our D flip-flop. Okay, and using the terminology latched for the output of the flip-flop might seem confusing because it's not a latch, it's a flip-flop. But the latch really just means that that value is stored at the output and is held there, is what we mean by latch. So, okay, but let's look at that same diagram, but let's look at it from a little bit different perspective. So I'm going to grab another figure from the notes, figure 1.20. Okay, let's stick this figure in here. And you'll note that this is actually the exact same, or nearly the exact same figure as above here for the latch. Okay, so you know, we're comparing it to this figure here. I guess it's fairly different, but anyway, this is looking at the latch as a storage device. Okay, so here's an example of the D latch used as bit storage. Okay, so what is different about this? Well, really nothing, right? We see that while the device is enabled, right? So when the enable signal is high, then at that point the output just follows the input, right? And we see that again here. When the device is enabled, the output simply follows whatever the input is. We notice some transition time being shown here, right? These slope lines just to show that this is not an ideal type device that changes instantaneously, because that is never true in a real device. It takes some time. Okay, but the key difference that we're trying to point out here is, rather than talking about the device being latched when we're in this disabled state, right? So again, let's go up and look at above here. We said that when the enable signal was inactive, we were latched, right? Enable signal inactive, the data was latched or stored on the output. Okay, look here. When the enable signal is in the inactive state, what are we saying here? We've actually stored a value on the output, right? again, looking at the second case where the enable signal goes inactive, we have stored that value that previously got written into the written to the output. Okay, so walking through this again, we have our data signal that is low. At this point in time, the enable goes high or active and then back inactive. That we can think of as writing the value of D to the output, right? So we have the value of D. The value of D gets copied to the output. So in this case, it's a value of 0 here. Okay, and then the next time a write signal occurs, so here this is a write, which is basically the enable signal becoming active. When that write signal occurs, that causes my value that's at my input, which is a 0. This gets written to the output, and as soon as my enable signal goes back inactive, that value gets stored and is held or latched at the output. Okay, so that's a D latch used as storage. Okay, so now we can picture the latch as a memory device rather than you know, well, I don't know what you might think of a latch as otherwise, but we can start to imagine this being used as memory in a computer system. Okay, so that's looking at a latch as a single bit memory storage device. We can, of course, do the same for a flip-flop. So let's look at the same diagram for a flip-flop. So bringing in the timing diagram, figure 1.21 from the notes. You'll note that the timing diagram here is basically identical to the timing diagram for the latch. Okay, so here we have a D flip-flop as storage. Oops. And again, note there's very little difference here other than the fact that the output can only change on that rising edge. Okay, so it's only at these instances of the rising edge. This is a rising edge triggered flip-flop. It's only then that the output can change, right? So whatever value was on the input gets copied to the output, right? And then again here, whatever value was on the input gets copied to the output. And it's immediately moves into the storage state or the latch state, right? So where up above here, right, up above, we noticed that it was only once, you know, it was only once we went back inactive, right, when the enable signal went back inactive, that we actually entered the stored state. While here, and with my D flip-flop, I enter the stored state immediately as soon as, you know, immediately after this rising edge has occurred. I'm back storing the value. Okay, so the behavior might look identical. You know, looking at these timing diagrams, they look identical, but the key difference here is being, you know, imagine looking up at this diagram on top here, if we were to stretch out this write signal, the value at the output would only get stored when the write signal actually went back to the inactive state. Where with my flip-flop, my edge triggered device, it's stored immediately. It's stored immediately on that rising edge. Okay. Let's extend this idea. So here we have, you know, really nothing new. We're just showing these, the latch and the flip-flop used as a 1-bit storage device, but why stop there? We generally don't want to store just a single bit. We often have the need for storing multiple bits. So very easy to extend that. So if I grab figure 1.22 from the notes here, here's an example of a D flip-flop being used as multi-bit storage. Okay, all we've done here in this case is we've used 4 individual flip-flops. I could number them if you wanted here. And what's my... Okay, so I could number these 0, 1, 2, 3, for example, to maybe represent the bits that they are holding, bit 0, 1, 2, and 3. And again, you'll see that the only kind of thing we've done to kind of coordinate them all together is we've used a common write signal or clock line that is shared between all of them, right? So when that rising edge occurs on the clock line, which we've now called the write signal, like we did in the previous example, all 4 flip-flops will get triggered to store the data from D out to the output Q simultaneously. Okay, so let's look at the timing diagram for this device. Okay, so if we look at the timing diagram for this, you'll see there's not a lot different from our timing diagram above. In fact, the write signal looks very similar. We see, maybe I'll zoom out here a little bit. We'll see 2 write signals. We see a data signal that's changing at some point in time, in this case labeled as D, and we see that the value of the output changing in response to each of those write signals. One of the major differences here, though, is, and this may be a new concept for you, is this idea of representing multiple bits with a single kind of line or waveform in our timing diagram, right? So this D with the 4 in brackets is indicating that I'm representing 4 bits with these lines. So what I'll do is I'll show my 2 lines, right? Because of course I've got 4 bits, so I can't represent the state of any 1 bit with a line. So I'll just show both lines, and between the lines I'll show what the value of each of those 4 bits. And anytime those values change, I'll show a cross in the line, just showing that the data values are changing, and in this case they changed to 1101 at that point, labeled by D. Right. The same thing for my output. My output now, this Q output signal that's shown on my diagram isn't representing a single bit. It's representing all 4 of these bits from each of the 4 flip-flops. Okay, and again, I note that there is no value shown here because I don't know what that starting value is, and I don't necessarily care. At this point, I know my values because they are stored in response to a write signal. Okay, so when this rising edge occurs on each of these flip-flops, right, rising edge triggers each of these flip-flops to take the value in D and copy it or store it out to the output Q. Okay, so I see at this first rising edge here at label B that this value 0110 gets stored to the output Q. And then at my next rising edge, I get the value that's at the inputs D 0, 1, 2, and 3. And in this case, it's now 1101. As soon as this rising edge occurs, that value gets copied out to the output Q0, Q1, Q2, and Q3. And that's being represented here, right? Where this is Q0, Q1, Q2, and Q3. Okay, so pretty simple extension of a single bit diagram. We're just using our data waveforms to represent multiple bits, and we write in between the two lines what the value is of each of those bits. Okay, while we're on the topic of using flip-flops or latches for other purposes, and in this latest case being storage, let's talk about some other very common applications of, well, in this case, a flip-flop or multiple flip-flops, for example. Flip-flops, a series of flip-flops, if we feed the output of one flip-flop into the input of the next flip-flop, they can act as a shift register. Okay, so in this case, let's label these flip-flops. Maybe this one represents bit 3, bit 2, bit 1, and bit 0. And what happens with each clock edge, the value that, well, with each clock edge, the value of D gets copied to the output Q, right, as we've been stating. But what is happening in this case, whatever value was on the input of this with the clock edge is going to get copied to here. And whatever value was on this one, right, was on this line, is going to get copied to here, right? So let's think about this. Let's put a example value maybe in here to begin with. Let's say that I have a value in my flip-flops currently where let's say that we're always feeding in a 0 here. Okay, and so we have this, maybe I'll show it like this. Maybe this input is permanently tied to ground, which is 0 volts, which is the equivalent of a binary 0. And let's say that the flip-flop starts off with a value of 1100 stored in the 4 bits of the flip-flop in our shift register here. Okay, so let's think about what happens with each transition of the clock. Okay, so if I'm gonna show each transition. Let me assume the first transition. I'm just going to show it with purple here. Okay, so with that first transition, this value of 0 gets copied to here. This value of 1 gets copied to here. This value of 1 gets passed through to here. This value of 0 gets passed through to here. So after that first clock edge, my value on my output becomes 0, 1, 1, 0, right? Each of the original bits got shifted one spot to the right. Okay, and let me maybe pick another color here. On my next clock edge, same thing. My value gets here my value is all permanently 0 here, so that value of 0 gets shifted through here again. This previous value of 0 gets shifted through to this side. This value of 1 gets shifted through to here, and this value of 1 gets shifted through to here. Okay, so we see this by these values, this 1 1 first clock cycle got shifted through one spot to the right. Next clock cycle got shifted through again one spot to the right. Okay, so we could set up the circuit to shift to the left as well, but let's think about what's happening here for a second. We started out with a value initially of 1100, and that's in base 2. In binary or in decimal, that is a value of 12. Okay, and we said after the first clock cycle, after the first shift to the right, we ended up with a value of 1100. Well, that's equivalent to a value of 6 in decimal. And then with the next shift to the right, we ended up with a value of 0011 in binary, which is equal to a value of 3 in decimal. So what you will note here is that with each bit shift, we're doing bit shift to the right, we're doing a divide by 2. Okay, so divide by 2 with each bit shift to the right. Okay, and this, we could have thought about this this shift register in the opposite sense. For example, let's put it in here again. Oops. Still, yeah. Let's using the exact same circuit, but let's now assume that the bits are, each of these registers represents the bits in the opposite order here. Okay, so what if this bit represents 0, the least significant bit, this represents 1, and this represents 2, and this represents 3, right? So this might be a little bit harder to appreciate here, but I'm picturing this as representing the least significant bit. So let's put in initial value in these registers again. Let's assume that we're going to start with a value the same as above here, where we had a value of 1 1 1 0 here. Oops, sorry, actually we had 1 1 0 0. Okay, but now I'm saying that first one is representing the least significant bit of our 4-bit value, and then this one is representing the next least significant bit, and then this one is representing the next bit, and so on. Okay, so now when I think about a bit shift occurring, now my bits are being shifted essentially to the left rather than to the right. I know the diagram's drawn in the same way. We could mirror that diagram if you wanted to think about it the other way, but it really doesn't matter. I don't know. Can I mirror it here? Not obviously here. Okay, but when I start generating my clock cycles now, maybe I'll assume my first clock cycle is an orange. This bit gets shifted now, what is essentially to the left based on this diagram. Okay, this bit gets shifted to the left. This bit gets shifted to the left with perspective to my bit field here. Okay, and I guess I should have shown that the input was maybe grounded again, so a value of 0 also gets shifted to the left. Okay, so that results in after that first shift a value of 0, 1, 1, oops, and this should have been a value of 0 in my bit field. Okay, so my 4 bits now have been shifted one spot to the left, so my value becomes 0, 1, 1, 0. Okay, and I could, just like the last time, I could shift these one spot to the left again. So shift in value of 0 again here, shift this one over, shift this value over, shift this value over, and now I have a value. Again, each of these values got shifted one spot to the left, so I have a value of 1, 1, 0, oops, 1, 1, 0, 0. This other 0 being brought in from the fact that the first flip-flop is tied to ground, just like in this case here. This gets brought in from the fact that we've got the input is equal to 0. Okay, so looking at these values here, let me just take this out of here, and equating them to their decimal value, we started with a value of 3 in base 10. One shift to the left, we had a value of 6, and another shift to the left, we had a value of 10. So what we are seeing here is that here we did a multiply by 2. Okay, so here we multiply by 2 with each bit shift to the left. Okay, and you can take any binary value, and if you take all the bits, shift them one spot to the left, you can convince yourself that you're multiplying by 2. So you may be thinking, okay, who cares? I already knew that this was the case, but we want to think about this from the computer organization perspective, and it turns out that having a device like a shift register in your hardware allows for very efficient multiplications and divides. You can look up the number of clock cycles that is required to do a division in a processor, and you'll see that it may be many clock cycles. But if you are capable of, or you can set up your code such that it's can work purely with divisions of 2, you can accelerate, speed up your application quite significantly if you can use a bit shift rather than a divide operation. And again, depending on the processor. So while we're on the topic of other applications of maybe multi-bit applications of flip-flops, another example that maybe you're already familiar with would be a configuration like this where we use multiple flip-flops to act as a counter. So we can with each clock cycle, with this particular configuration, and you can, I encourage you to prove it to yourself. You can show that the bit sequence will increase with each clock cycle such that we'll get a binary count from 0 to, well, in this case 15, decimal equivalent of 0 to 15 with each clock cycle. So again, I encourage you to convince yourself that that is in fact true. While we're on the topic of kind of multi-bit devices or using our flip-flops for multi-bit applications, I think it's important to remember that we often use many bits. We'll often call that n number of bits, are often used in a group that we refer to as a word. And in this way, we can represent many more things or states. States or anything in general. Okay, the number of states that we can represent with binary values is equal to 2 to the power of n, where n is the number of bits. Right, so again, maybe review for most of you, but it's worth remembering. So with 2 bits, so 2 to the 2, 2 to the 2 says we should be able to represent 4 things. And well, yeah, we can represent 0, 0, 0, 1, 1, 0, 1, 1. So we can represent 4 different values with 2 bits. With 3 bits, right, 2 to the 3 says that we should be able to represent 8 things with 3 bits. Right, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right, so we can now represent 8 different unique states, or 8 different unique things using 3 bits. In the examples above here, with our our 4-bit storage, using whether it's flip-flop or latches, well, now with 4 bits, of course, we can represent 16 different things. Right, 2 to the 4 equals 16, and we can represent 0, 0, 0 all the way to 1, 1, 1. And we showed that this is where as we get into more and more bits to represent our data, this is where it becomes useful to use hexadecimal, right? So this value in hexadecimal would be equal to, let's say, 0x0. This value would be equal to 0xf. I'm using the 0x as one of the standard ways of representing hexadecimal, right? This is base 2, this is hex, or another way you might see it is I use 0 with a base 16, or f with a base 16, or sometimes you'll see 0 with a little h subscript, or f with a h subscript, sometimes a capital H, sometimes a lowercase h. All of those forms are representing base 16 or hexadecimal, right? The equivalent of this, of course, in decimal would be, well, of course, this is still equal to 0 in base 10, or this would be equal to 15 in base 10. Okay, but continuing on, 4 bits, sure, we can represent 16 things, but one of the most conventional number of bits to use is 8 bits, which is known as a byte. And, oops, a byte. And of course, 2 to the 8 is equal to 256 different things or states that we can represent, right? 0, 0, 0, 0, 0, 0, 0, all the way to all of those values being 1, right? Which again, we could represent, well, in decimal, this would be value of 0 all the way to a value of 255 in base 10. In hexadecimal, this is equal to 0x00 or 0xFF. Okay, when we get very large binary numbers, it can be challenging to equate them to the decimal equivalent, which is how we tend to think. We're brought up to think in base 10 and decimal. But some quick tricks that you might find helpful is to remember some of the key number of states that can be represented by 10 bits. So 10 bits, this is an easy one to remember, can represent 1,024 states. Okay, or we may call this 1K in the digital world. Okay, doubling that 2 to the 20. This in the digital world is the equivalent of, well, 1024 times 1024, which is 1,048 272. Sorry, not 272, 576. But again, that gets difficult to remember so often. Instead, we say, well, this would be 1K times 1K, which is 1 meg. Okay, and again, we have to remember that this 1 meg in digital representation actually is equal to a little bit more than 1 million. Okay, and it depends on the type of, you've probably discovered this. You have bought a hard drive that says that it was, let's be unrealistic, or and says it was a 1 megabyte hard drive. Well, that they're giving you a value in decimal, and then you plug it into your hard drive or into your PC, and your PC quotes a value based on 1 megabyte in base 2, where 1 megabyte is equal to this value, and all of a sudden it seems like you have less storage available. Okay, so it's gets a little bit confusing when to know which base system is being used when you just see 1K or 1 meg being used. This is kind of this topic's kind of being drawn from chapter 6 of the notes, but it's good to remind how to do these conversions between the different base systems now, because you're likely going to need it in the lab very soon, particularly the hexadecimal or the base 16 values. So let's look at some means of converting between binary and the different bases. Okay, so let's take a binary value. Let's start with a value of 101 101 110 001 111 110 110. Okay, so right away in base 2 we see that's a very overwhelming number to represent. It takes a lot of time just to enter that number. So there must be better number systems or better bases to represent this in. We haven't actually talked about it yet, but one number system or base that you may come across in the digital realm is base 8. Okay, so everything looking at powers of 2. So base 8, or otherwise known as octal, you may come across. Base 8 has, as it sounds, 8 different states. We can have a value of 0 to 7 represented. Okay, to convert between octal and to binary and octal, we just take our binary values and split them up into 3-bit chunks. Okay, and then we write what the equivalent value is for each of those 3 bits. Okay, so and base 8, converting between binary and base 8 is the same as converting between binary and decimal. The only difference being is we can't go above 7. So if you're not aware of how to convert between binary and decimal or base 8, you remember that each bit represents 2 to the value of 0 times whatever the value is in that location. So here we have 0 times 2 to the value of 0. That gets added on with 1 times 2 to the value of 1 because we're in the 1 position, and this 1 times 2 to the value of 2. So here we have 0 times 2 to the value of 0. So because it's multiplied by 0, it's 0. 2 to the value 2 to the power of 1 is going to be a value of 2 times 1. So we have this. Okay, so maybe I'll put these up above here. This one's going to be equal to 0. This one's going to be equal to 2. And then we have 1 times 2 to the power of 2. This is equal to 4. So all of that sums to a value of 6. Okay, you might find it easier just to remember these conversions because you convert back and forth quite a bit. So this is the value of 6, value of 6, value of 7, value of 1, value of 6, a value of 5, and a value of 5. Again, if you want to see how these conversions are done, you can see that in chapter 6. In fact, there's I'll give you a table here that shows an example. And here's an example of converting between a binary value to a decimal value. Okay. So again, base 8 is essentially the same technique, except with base 8 we never have more than 3 bits represented at a time. Okay, because we can only go to a value as large as 7, as we see represented in this case here, where if all bits are high, that's the highest octal value we can get is a value of 7. Okay, let's take this same value that we have up above here and let's convert to hexadecimal. Okay, so 101, 101, 110, 001, 111, 110, 110. Okay, base 2. So to convert to hexadecimal, remember that hexadecimal is base 16, meaning we can represent 16 different values. Oops. So we need 4 bits to represent 16 different values. So we just take our binary value and we chop it up into 4-bit chunks. Okay, and if we have a bit left over like we do in the front here, we can just treat it as though there were zeros in the most significant bit position. Okay, so we'll come back and look at that in a second. Okay, here again I presented the binary to hex conversion table, but you can also use the kind of the same technique as above here if you want. The only problem is it becomes less clear once you go above a value. So now hexadecimal can represent values up to 15, the equivalent of 15 in decimal. So what do we do when we go above 9? Well, the values we have to know what the corresponding value is to 10, which is A, and 11, which is B. Okay, so here it becomes helpful to remember what the hexadecimal lookup table is for these, or to remember them. So here's a value of 6 in hexadecimal. This is a value of F. This is a value of 3. Here we have a value of E, and here we have a value of 6. And again, here if I assume that there's zeros on the front, this is simply a value of 1. Okay, and again, this is base 16, whereas this is base 8. So we have the same number represented 3 different ways. Okay, so each of these numbers is identical in the weight that it holds, except here it's represented in base 2. Here's the number represented in base 8. Here's the same number represented in base 16. Okay. So converting back and forth between binary, octal, and hex is fairly straightforward. Here I've shown how to convert between binary and from binary to decimal. I encourage you to remind yourself how to convert back from decimal to binary. Here's that same value from above, the same value of 181 in decimal that we start with here, 181, 181, and we've converted it back to the binary equivalent, right? And that's done through a continual division by 2 because we're converting to base 2, and using the remainder value to fill in the binary values, and the remainder value is built up, or builds up the binary value from least significant digit to most significant digit. Okay, so this bit is least significant and so on, and this bit being the most significant. Okay, so have a look at chapter 6 if you don't remember how to do those various conversions. I'll post a little practice review sheet on this topic, as well as timing diagrams for different logic gates, both combinatorial and sequential.